What you have found so far is that when you're like solving for the square root, they have been kind and they have given you something that is a positive number in the root. But if I were to say that x squared were to equal something like -4, and you take the square root of both sides, we have an issue, right? The issue is I can't take the square root of -4. And so what imaginary numbers do is they define the square root of -1 for us, all right? And so they say, well, you can't take the square root of -4, but you could take the square root of 4, and then you could move on with this problem if we could just take the square root of 4. And so what they do is they define the square root of -1 by assigning it a variable. It's not really a variable because it's always the same thing, but they assign it a definition. It's the imaginary number I. All right, and so we move from the real numbers that we've worked with like our entire life to complex numbers, which include square roots of -1. So imaginary number I is defined as the square root of -1. So if you have the square root then of -1, you can just pull that out and say, well, that is going to be I. And so I can say, well, square root of -4, well, that is the square root of -1 times the square root of 4. That would be the square root of -4, yes? And since I have defined this guy as I, and I already know what that is, that's 2, then that means that the square root of -4 is going to be 2i. The square root of whatever's inside times the square root of -1, which is defined as I. All right? And so that's what they are telling us here. All right? That's what they're telling us here. So we can now move on with the problem and solve it using imaginary number I. All right, so let's look at example 1. Simplify the square root of -8 by using the imaginary I. And so what we're going to do is we're going to say, well, I have the square root of -8. I'm going to go ahead and take an I out. And so then I have to only worry about +8. And if I'm going to simplify that, I'm going to use my factor tree here. If it pairs up, when I'm looking for square root, it can come out of the root. If it does not pair up, it needs to stay in the root. All right, I took the -1 out of the root with the I. So on the outside, I have an I. I'm going to have a 2 from this pair. And inside the root, I'm going to have a 2 from that one that is just single. And so my answer to this is going to be 2i square root of 2. Whereas just the square root of 8 would have been 2 square root of 2. The square root of -8 is going to be 2i square root of 2. You simplify it the same, you just take an I out considering the square root of the negative. All right? If it doesn't have a perfect root, so let's say I have the square root of -5, I would just say I times the square root of 5 to simplify it. All right? So go ahead and try A, B, and C there. All right, so now we introduce what's called complex numbers. Complex numbers combine real and imaginary, all right? You have a real part, which is your A here, and you have an imaginary part, which is your BI. When you write a complex number, this is standard form, meaning the real part needs to come first and the imaginary part needs to come second, or you will be writing it out of standard form. And so all of the answers that you give me should be in standard form. Your real plus your imaginary. Think of it like different variables. You cannot combine real and imaginary numbers, okay? So when you're combining complex numbers, you can combine the real parts of them and you can combine the imaginary parts of them, but you can't combine the real and imaginary together. So this is why it will be in this form, A plus BI, the real part plus the imaginary part. It'd be like adding X and Y, X plus Y. That would just be how you would leave it because you cannot combine in the x and the y, okay? You can also think of the b as a coefficient. So if you're adding different parts of your imaginary, you can just add the coefficients, all right? You have 5 square roots of -1 and 4 square roots of -1. You have 9 square roots of -1. So if you have 5i and 4i, you have 9i, okay? And so you can think of it that way, all right? And so like this first one is just writing it in standard form. Simplify this imaginary number. Write the complex number, the square root of -9 plus 6 in the form a plus bi. The first thing that we would need to do here is we would need to simplify this square root of -9. Well, square root of 9 has a perfect root, which is 3. So we would just write this as 3i. But that is not in standard form. The real needs to come first and then the imaginary. So we would rewrite this to 6 plus 3i. That is standard form for that. So go ahead and rewrite this one, negative square root of 18 plus 7 in standard form. Simplify your imaginary part and then rewrite it in standard form. All right, so we are used to this left side of this right here. Natural, whole, integer, rational, and real. And then, of course, we have irrational that's kind of in this mix. And this is where we have stopped so far in our math life, right here. Set of real numbers. And so real numbers includes all the numbers you normally work with, right? And then now we have thrown imaginary in. And so this group here, our universal set, then becomes the complex numbers. It includes our real plus our imaginary, all right? And so then all of a sudden, instead of a coordinate plane that we're used to, which is our real numbers, our xy coordinate plane, we have a complex plane, a complex number plane. So instead of x and y that we're accustomed to, we have the real numbers and the imaginary numbers, okay? Real numbers and the imaginary numbers, all right? And so if I were to look at 3 minus 4i, I've moved 3 spaces on the real axis. I have moved 4 spaces on the imaginary axis, right? And so if I were finding the absolute value is the distance from 0. That's how we define absolute value in the real number world, right? How far away from 0. Except I have moved 2 dimensions here, right? I have moved 3 in the real and 4 in the imaginary, okay? And so if I want to find the absolute value of this complex number here, I'm actually going to use the Pythagorean Theorem to do it. Pythagorean Theorem says a squared plus b squared equals c squared, right? So I've created this right triangle. A squared plus b squared, right, should equal c squared, which is my hypotenuse. And so that's where they come up the formula for the absolute value. You just take your real and you square it. You take the coefficient of your imaginary and you square it, okay? Add those up and take the square root. This is basically the distance formula or the Pythagorean theorem. That's really all it is. And so you don't have to recreate it and you're not going to have to graph it, all right? What you do have to remember that is if I ask you for the absolute value of a complex number, you need to square the real part and the imaginary part, add them and take the square root. It's based on the Pythagorean theorem. So it's simple to do, just showing you where it came from so you can remember the formula. So let's look at this example here, example 3. Find the absolute value. Well, when it's like this, it's pretty straightforward. What is my real part? 0. So I have 0 squared plus what's my imaginary coefficient? 5 squared. And I take the square root. So it ends up being the square root of 25, which ends up being 5. So if you just have an imaginary part and you want the absolute value, you've only moved one direction. It is the distance from 0, which is going to be 5. You don't even have to use the formula. Just like if I had just a real part and I wanted the absolute value, it would just be the distance from 0, which would be the real part, okay? So the difference is that you are going to, it is absolute value, so your distance is always going to be positive. So if that were negative 5i, that would just be 5, right? Let's look at the next one. I do have a real part here. So what's my real part? 3 squared plus what's my imaginary part? Negative 4 squared. So I'm going to have 9 plus 16 here, which ends up being actually the same exact absolute value. All right. It's easy. Just remember how to do it. Try those 3. I really want to talk about additive inverse really quickly, just for adding and subtracting purposes. And then we're going to add and subtract these and multiply them as well. So additive inverse, the reason I want you to do this is because there are times when you're going to subtract complex numbers. And so if they want subtraction, then you would just distribute a negative through. So if I were to subtract this particular one, it's the same thing as just distributing a negative through. And so negative 1 times negative 2 would give me positive 2. Negative 1 times positive 5i would give me negative 5i. And so additive inverses, if you were going to subtract them across, it's just going to change both signs of your group. That's all an additive inverse does. And we're about to do subtraction, and so they're just showing you distribute the same way. So let's look at example 5. Adding complex numbers and subtracting as well. So when you add complex numbers, it's just like when you add polynomials. You add your like terms, meaning you're going to add your real portions and add your imaginary portions. So for this one, I have 5 plus 7i plus negative 2 plus 6i. So I'm going to add my real part, 5 plus negative 2. And then I'm going to add my imaginary parts, 7i plus 6i. All right. If I were subtracting like you're going to do on B, you're just subtracting each piece, or you can distribute the negative and just combine your like terms. So go ahead and do A, B, and C really quickly. I squared, right. So if I said 5i and negative 4i, you're going to say 5 times negative 4 and I times I. But I is actually defined. What is I? The square root of negative 1, right? So if I say I squared, I'm saying the square root of negative 1 times the square root of negative 1. What happens when I multiply a square root by itself? It's itself. So the square root of negative 1 times the square root of negative 1 is just negative 1. Which means in this particular problem, I actually have negative 20 times negative 1, which means I have what? Positive 20. That is my answer. We're going to do foiling the same way. We're just going to simplify at the end. All right? So we're going to say 2 times negative 3. 2 times 5i. 3i times negative 3. And 3i times 5i. Okay? So far, so good? Now, I can simplify a couple things here. First of all, positive 15 times I squared is going to be what? Positive 15 times negative 1. So this is going to become just negative 15. We're going to lose the I completely. Okay? And then I have some like terms here, 10i and negative 9i. So my 10i and negative 9i combine to just 1i, right? Okay? And then, if you'll notice, I also have, now that I have simplified the 15i squared, I have negative 6 and negative 15 that can combine. What's negative 6 and negative 15? So in standard form, the real part is negative 21 plus the imaginary part, which is just I. Right? Make sense? So we just did solving by taking the square root, which is perfectly fine on all the ones they gave you and all the ones that I gave you because you had a positive square root. In solving by the square root, my first goal is to get x squared by itself. So in this one, I'm going to subtract my 100 first, right? So I'm going to take this, subtract 100 from both sides. I will get 4x squared equals negative 100. And then I am going to divide both sides by that 4. So I get x squared equals negative 25. Here, my process is to take the square root of both sides, all right? Square root of both sides. Prior to this section, your answer would be it does not exist because we're talking about real numbers only. Now we've introduced complex numbers, and all of a sudden we have an answer for this. The square root of negative 25 is going to be what? 5i. However, when I am taking the square root with a variable, I have to also consider the negative root. So it's positive and negative 5i, right? We don't want to forget the positive and the negative answers there, right? Positive and negative answers are very important. Yes.